Hey students, in this video I'd like to go over the line of best fit practice with you. So number one, we're exploring infant weight as they compare the pounds that the infant weighs as their age progresses in months. So we'll start with part A. What age did the infant weigh 11 pounds? So here's 11 pounds. There's a data point right there at 3 months. Part B. What was the infant's weight at birth? Well, at birth, you're 0 months old, and there's a weight data piece right there between 6 and 8, so that'd be 7 pounds we would estimate. Part C, drawing a line of best fit involves choosing 2 points so that your line passes through the middle of your data. Well, I've chosen the 2 points for you, so all you need to do is take a straight edge at that point and connect it through that point with an arrow at the right because the baby's going to keep growing. No arrow necessary at the left. They're not going to age backwards. Part D, take those same 2 points and let's come up with our line of best fit equation. So first we need the slope. So we'll take the y values and subtract them from each other. And we get 15 over 12. And both those are divisible by 3. So if I divide both top and bottom by 3, I'm going to get 5 over 4 as the slope. Now, I realize one of these points is the y-intercept, but for this example's purposes, we're going to show you how to use point-slope form to come up with the slope-intercept form equation. So taking 0, 7 and putting it in for x1 and y1, and 5/4 and putting it in for m, we'll substitute into this equation. Y minus 7 equals 5/4 times x minus 0. Distribute that 5/4 through multiplication, and you'll have y minus 7 equals 5/4 times x. And 5/4 times 0 is 0, so we don't need to write that. We'll add 7 to both sides, and you'll end up with your final equation of y equals 5/4 x plus 7. So there's your line of best fit equation by hand. Looking at part E, we're now going to use that equation to make a prediction. We're going to predict the weight, which is the y variable, when the infant is 18 months, which is the x variable. So we'll write our equation, and this time we're going to put in 18 in place of x. So we can come up with that predicted weight. So multiplying 5 times 18, or you could simplify 18 over 4. Those are both divisible by 2. Or you can use your calculator. Crunch the numbers to come up with this predicted weight. All right, I've done some number crunching here, and I've come up with a prediction that this baby will weigh 29.5 pounds when they are 18 months old. Part F, does the data show a positive, negative, or no relationship? Remember, positive means your data is flowing up, negative flowing down. No relationship is your data is incredibly scattered with no pattern at all. Well, that graph was flowing up. This baby's growing, so we are showing a positive relationship in this graph. Part 2, girls and boys. We're comparing them, a relationship between the number of girls and the number of boys in 10 different classrooms. So studying this graph, what type of relationship, if any, does the data show? Is there a pattern to this? So looking at these points, I don't see a trend upwards or downwards. So really, it appears to be no relationship here between the number of boys and the number of girls. Is it possible to find the line of fit for this data? If there's no relationship, there really is no great line of fit. You might see one passing right through the middle sometimes like this. And that would be like y equals 11. But ultimately, there's no great line of fit when your data is scattered like this. C, is it reasonable to use this scatter plot to predict the number of boys in the classroom based on the number of girls? Again, since there's no relationship, there is no prediction to be made. Because remember, you use your equation of your line of best fit to make predictions, just like in the previous baby problem. All right, in part 3, we're exploring a scatter plot that talks about the cost of juice measured in dollars, depending on how big that juice is, measured in fluid ounces on the x-axis. So part A, reading the scatter plot. How much does a gallon of juice cost? So here is 1 gallon. You have to know how many ounces that is. So let's look that up real quick. All right, after looking that up, it was determined 1 gallon is 128 fluid ounces, or this point right here, and that would be a cost of $12. So I'd ask Siri there for a second. Part B, how many fluid ounces of juice can you purchase for $3? So go to 3 on the y-axis. It looks like we can get somewhere between 12 and 24. If you want to estimate that to be about 20 ounces, that OZ for ounces, that'd be okay. Part C, okay, your answers might vary here depending on the points you picked. So we're going to pick 2 points so that when we draw a line, that line will pass through the middle of our data. So let's say we pick these 2 points right here. The next thing I want to do is estimate those 2 points. So let's estimate that first point to be about 20, 3. And the second point, that second star right here, let's call that 64, 7. And then draw your line through those 2 points that you just wrote on the graph. So as best you can, you want to draw a straight line through those 2 points with an arrow at one end. Great. Part D, write an equation. So the same thing we did in number 1. This time we got to find the slope. So we'll start with that. M equals, subtract the y values, and then subtract the x values. So that'll give us 4 over 44, or 1/11. Next, write down that point slope form. That's going to come in handy. And then we're going to plug in the numbers into point slope form. Let's call this x1 and this y1, and we're going to plug it in right here where you see an x1 and a y1, and we have the slope. So I'm going to pause this and fast forward these calculations to save time. All right, I've crunched the numbers and come up with 2 equations. One's an exact equation, which is always great to have, leaving it in fraction form. And then one's an approximate equation right there. We're going to use this to make a prediction in the next step. All right, there's our equation, and they want us to predict the cost, which is the y value, when we have the x value of 256 fluid ounces. So we're going to plug 256 in for x, crunch the numbers, and predict a cost. Go ahead and let's do it. All right, letting the calculator do the heavy lifting, we came up with the approximate cost of $24.45 if you're going to buy a 256 fluid ounce container of juice. That's a lot of juice right there. Part D, does this data show positive, negative, or no relationship? Well, does this go up, down, or was it scattered? I believe this graph increased from left to right, which is positive. In the last practice problem here, you're studying the cost of admission as age increases. So taking a look at this, our first job is to say, what type of relationship is this? Is it going up? Is it going down? No, neither. So there's no relationship here then. We can draw a line of fit. That just means do your best to draw a line passing through the middle of your data. So there we go. And an equation for this line, since it's just horizontal, the slope is 0. So we'll put that next to x. And the y-intercept is about 4. So we'll just call it about y equals 4. And last part is interpret the relationship. It looks like the cost stays the same no matter what age you are. So that would be interpreting the cost and the age compared to each other. It stays the same no matter what age.